Thanks, Gilpy. This is on. Yep, this is on. So my name is Ben. Thanks for the introduction. I'm going to be talking to you guys about AIware Observability. So, if this thing works. Maybe. Are we not connected?
Try the clicker now.
Perfect. Okay. All right. So quick overview. So we're going to quickly go over what is observability. We're going to talk about observability in traditional software systems, right, which we're kind of referring to as operational observability, and how that applies to existing AIware. We're then going to go into why that's not necessarily enough, so some of the challenges that comes with observability in the context of AIware, and discuss cognitive observability, which we sort of start to come up with to begin addressing some of these challenges. And then finally, we're going to talk about Watson, which is a framework for reasoning path observability. This is some work we've been doing recently to begin to address some of these challenges. Now, so every time I'm working with observability, right, I'm reminded of this comic. So this is a comic from 2008, right? Some of you might have seen it, some of you might have not have. But so the only valid measurement of code quality, WTFs per minute, right? So good code, pretty quiet. Bad code, it's kind of loud, right? So the idea here is that you don't really know what's going on. Now, if we're coming into AIware, right, this is just getting worse and worse and worse. You're not sure really what's going on. And so here, this is actually generated with Dolly. It took a bit of work to actually get something that was usable. But you see agentware code review, right? Nobody really knows what's going on. If you have agents generating code, it's kind of hard to see, like, why did the agent do this? But in AIware, this isn't just for code review, right? It's everything. So if you have agents that are working in a system and they're making some sort of decisions, you don't know why they're making these decisions. You're coming up with questions and you don't really get an answer from the agents after they've done it, why they might have made that decision. And so anytime I'm working with AIware, right, this is what I'm anytime I'm working with AIware observability, this is what I'm thinking of. How can I begin to explain or understand what the agent's doing, see what it's using for its reasoning processes, and how it's making its decisions. All right, so we're going to go into the session now. So what is observability? So when we're talking about observability, right, we're talking about the ability to understand a system's capabilities and behaviors by analyzing the data it produces. So after you've deployed an application, right, you want to be able to monitor it and see how it's performing. You want to be able to understand what's happening, why is it happening, where are potential problems, and then how is the system performing, right? So these are all things that you can sort of begin to build out in terms of observability, right? So you're trying to understand the system after it's deployed, how is it performing, what are the outputs, and why things are happening is really the answer, or the question that we're trying to answer. Now, traditional software systems, right? It's really quite easy to instrument traditional software systems to capture these outputs and the state. So a lot of times we're going to use assertions to verify program properties. This is very simple to do in code, so you just assert some condition, and then you can raise an exception based off of that. And you get a very concrete stack trace, right? You know what went wrong, you know where it went wrong, and the reason why it went wrong, right? And then we can sort of build this up. So we can capture different metrics, logs, and traces to sort of analyze the system's state, gather it, and analyze it in some sort of repo, right? So if we're looking at logs, same context as the example on the left, we can go through these logs, right? So we receive a request, see what's happening, calculate the square root for -1. We get an error. Number must be non-negative. What did we send for a response? What's happening, right? So we're able to trace through these systems. And so all of these methods are really effective because of that traceability, right? So we can trace the system behavior between the system behavior and the executed assets. In this case, it's going to be code, right? And developers are able to instrument these development assets, code, right, to track the execution flows, identify any of the bottlenecks, and then trace issues back to their sources to resolve them, right? It's very easy to do with codeware, essentially. And then, so this would be an example of what would essentially be an observability platform for traditional software. So you can see we're able to gather up all the logs that are being generated by the system. We're able to see the usages, so hardware resources, memory usage, disk space, that sort of stuff. And then so also the traces, right? So once these systems are actually executing, we're able to trace through the path of execution that these systems are taking, right? So that's what we're talking about with just in the context of traditional software systems, right? A lot of what I just mentioned would be what we consider to be operational observability. So now that we're moving to AIware, right? Everything we just talked about, that's a good place to start, okay? So we're essentially, in these systems, we're trying to observe what happened, right? We're able to gather or monitor different metrics and system status through logs in these systems, right? Systems, traces, performance counters. Because these AI systems, right, they're still generating data, right? They're still generating logs. We're still interacting with the system, or the agents are still interacting with different parts of these traditional systems. And we still gather this information into our observability platform and then see how they're performing. So this is actually the dashboard from Traceloop. So they have an observability platform. Again, it's strictly operational observability. So you can see they have some LLM-specific stuff, right? So what models are being used, the tokens per minute, requests per minute, latency, the price of using these models, and then some other, pretty base metrics. But as a start, right, it still provides a comprehensive view of the interactions between systems and the components. And then once we get through complex workflows, it does give some observability into how these AIware systems are performing. So we go a bit deeper into what we're talking about with operational observability, right? The basics are going to be logs and execution traces. Like I said, you're going to want to be logging every interaction with the agents, and then collecting what you can from the interactions with the agents. So collecting what you can from the agents, and then actually tracing, the execution of these programs. So if we go at the very base level, right, you might have a run, and a run is just one single unit of work. So you might have a question that's being sent to a vector database that does some indexing and generates some embeddings, and then the next unit of work would be, you take these documentations, generate and then do some sort of generation and receive an answer, right? So these would be examples of runs. A trace is a collection of runs, okay? So you can think of just a trace as being some sort of execution workflow, and then the project would be any sort of execution of that workflow you have. So to sort of build up these abstractions as you go along. And really, it's a bit further than just going beyond plain API monitoring, like what you do in traditional software systems. So you want to be able to actually collect more than just requests and errors, right? So you want to be prompts, responses, costs, token usages like we saw in Traceloop. And that sort of begins to give you some deeper insight into the prompt evaluation and model performance. And we're sort of moving beyond, just sort of tracing through the execution of these traces, right? So we're trying to look into the foundation model functionality and its actual performance within the application. So once we have these logs and traces, right, we're going to want to make sure we're gathering any sort of metrics, resources, and LM tool monitoring, metrics that we can. So basic thing we're going to be gathering here, volume metrics. That's one of the main things that we want to be tracking, right? So we want to be tracking how many calls are going to specific foundation models in AIware, how many are going to be working successful, how many are going to have errors, and then also how long these take, right? So we want to be tracking the latency metrics as well as the token metrics. So these are sort of the basic building blocks with tracking any sort of foundation model, AIware observability. Once we have those, we want to be actually tracking what resources they're using, right? So we saw in Traceloop that it was tracking which CPU it was using, so the example I showed previously, which CPU it's using, what hardware it's using, what GPU it's using, NPU using, basically the hardware that it's running on, and then any sort of tools that the foundation model is using. We had mentioned before, we're sort of moving into agents using tools. That's something that we need to make sure we're tracing, how these foundation models interact with the tools to see how they actually use them, whether they're being effective, and how we can actually improve them in the AIware architecture. So if we look at state-of-the-art observability tools, right? This is a list of a couple main ones and sort of what they're mainly geared at, right? So we can see volume, latency, tokens, and resources. A lot of them are, so like I said, a lot of them are going to be getting volume and latency. It's kind of a mix on what they're actually collecting with latency. And a lot of the time it's just simple stuff, right? So LLM latency, trace latency, things that are really easy to instrument. Tokens as well, nearly all of them are going to be tracing tokens, and then from tokens we can actually get to resources, right? So the cost of, excuse me, so the cost of actually running the LLM call, and then as well the cost of using the hardware underneath it, right? And so all these state-of-the-art platforms are really focusing on these low-level details. So they're just collecting traces and runs for the LLM calls, not really a lot of insight into what's actually going on under the hood of the agent itself. Now I will say there's just a note here. So there is a really good framework called OpenLLMetry. Some of you might be familiar with OpenTelemetry. So that's sort of the standard telemetry, I'd say like standard telemetry framework, I'll call it, that people are usually using in traditional software. So this is an effort to really try and standardize what metrics should be captured when you're instrumenting AIware for observability. So if we actually look at a concrete example, right? So if we just have a very simple workflow app. Sorry, I'm not sure. Oh, that's a camera. So if we actually have a really simple workflow app, right? So we're just given a topic, run a query for some knowledge on the topic, hand the topic and the query results to an agent to just create some bullet points, and then hand those bullet points to another agent to make a summary, right? And so I've sort of just, you have a query, agent, it's just abstracted away, not really, it's just an implementation deal at this point. But if you were to use trace loops library, right? Because we want to be able to instrument this application so that we get some sort of observability into it. They make it very easy. So all you do is just add these decorators to what you want to make sure is instrumented. So so a query, for example, would be a task. We would annotate the actual agent function just with the agent, and workflow with workflow, right? So they make it very easy to instrument. And then once we actually run the workflow, right? So we're able to get this trace. So this is actually up on Traceloop's observability platform, and we can sort of see as the topic summarizer executes, we get some very basic how long did it take. We'll see some other stuff here on the next slide. But then, so when we run the query, right? So this one actually goes and queries the knowledge base. Underneath the hood, I'm using ChromaDB. And so OpenTelemetry knows how to instrument ChromaDB out of the hood. So it's able to track any of the metrics that are associated with that call. With the agents, I was using the OpenAI API under the hood, so it automatically tracks that information as well. And then so when we go a bit deeper into it, right? So if we're looking at this OpenAI call, we're able to see vendor, model, what type, the tokens that were used, the cost, some of these basic metrics that I talked about before, right? And so this is sort of what a lot of these observability platforms are doing. They're all relatively have this feel of traces, logs, cost, usages. They're all sort of essentially doing the same thing in terms of operational observability. But we can't really stop there, right? Foundation models are becoming more complex. AIware becomes more complex. Requirements are shifting to higher levels of abstraction, right? So what we saw with operational observabilities, we can't really answer questions like what knowledge did the foundation model actually use when it was using the planning of the execution, right? It doesn't really show what led a group of collaborating agents to make a decision, or maybe they got stuck in a loop. These are things that are really quite hard to actually trace and instrument and get out of the agent and AIware systems themselves. Like I said, achieving this level of observability is really quite hard. And now, so I'm just going to talk a little bit about some of these challenges that actually focus on that and lead to this. So like I said, observability goes beyond traditional monitoring. You really need to get some deeper insights into the system's complex behaviors and the semantic outputs, not just any sort of inputs and outputs or logs. And this is challenging because AIware's unique functionality and outputs, they require more advanced tools, right? So we can't just instrument the call to OpenAI. We're not going to get that information back. And so I've sort of grouped these challenges into 3 different areas. So we're going to talk about each of them here. So agents, they have these abstract behaviors, right? And you can have these errors coming from, so you can have these errors that are coming from places that really lack any sort of code, right? So if we look at codeware, and what we saw, so for example, the assertions example I gave earlier, right? If you have codeware, and you run to your observability platform, you see an error, you can go back and trace that error to the exact spot that happened in the code. Agentware, that's really kind of difficult to do. So if you have your agentware that sends telemetry up to the observability platform, you see that some error happened, right? But you can't really pinpoint where it happened exactly, because there's limited code or documentation, and a lot of these decisions are made on the fly, right? And then not only that, so you're going to have these reasoning chains, right? So these errors are difficult to trace because they come from these complex reasoning chains and interactions in the agentware, right? There's not really any logic in the agent that you can expect to see like, oh, how was this decision made? Or it's just based on latent knowledge that's sort of embedded in the model, right? So we look at a concrete example from this. So a fraud detection system, right? If you have codeware, you can sort of build up this workflow that sort of you have a transaction data, right? Is the amount greater than 5,000? Yes or no? Is it from an unrecognized region? Yes or no? You end up with a final risk score. Is it greater than the threshold? Yes or no, right? So based on that, you can say, oh, I'm going to block this transaction or I'm going to allow it. It's really quite concrete to figure out where decisions are made and where things might have gone wrong. With the agentware, though, you're just handing the transaction data to the agent, and you're getting an answer. Is it blocked, or should I block this transaction or allow it, right? Which is fine. Like, you might have a really good agent that works really well with this. But if you get something wrong, so a transaction is wrongly flagged, you can't really figure out why was this incorrectly flagged or not. And so there's these errors, right, that just come up from these complex interactions. And there's multiple features that are learned by the agent that you don't really know why these final decisions were actually made. And then things just get worse and worse when you get multi-agent systems, right? So you can have these multi-agent systems that are all making decisions, and they sort of cascade down the workflow, right? So you have decisions made from one agent early in the workflow that are affecting decisions that are of agents later in the workflow. So if we look at this example, right? So let's just say we have this system design code generation workflow, right? So you have a conversational agent that's used to gather requirements from a user. That conversational agent would hand these requirements to a system design agent, who then hands these designs to a code generation agent, right? So let's say the conversational agent gathers that the user wants the code to minimize CPU usage in order to lower costs in the cloud, right? They hand that requirement to a system design agent, who's going to make the assumption that, okay, I have limited budget for CPU. That's the only requirement I have. So I'll assume that I have unlimited budget for storage, right? And so it's going to come up with the design of allocating 1 cloud CPU and then 1 million storage buckets, right? This is based off the assumptions it's making. And then it'll hand that design to the code generation agent. Code generation agent does exactly what it was told to do, does a good job. But then the user's left wondering, why does my code use 1 million storage buckets, right? And then they have to trace all this back through these agent workflows, right, to figure out why the decision might have been made. The key here is that we don't know why, these assumptions are not visible. We don't know those, right? We can't figure them out unless we have the agent actually including its reasoning process in its outputs. So these are all things that we can't really address with existing operational observability. So how do we move forward with it? What we're going to talk about now is cognitive observability. So cognitive observability shifts the focus from traditional metrics to more cognitive and linguistic aspects of observability, right? So this is emphasizing how FMware systems think and communicate, right? It gives us deeper insights into the system operations. So this is where we're kind of moving beyond traditional metrics, any sort of logs or tracings that we can get just by instrumenting the AIware, right? And so it really helps with understanding how agents in a multi-agent system are interacting with each other. So we're breaking this up into 3 different subcategories. We're going to have output integrity, semantic feedback, and then reasoning path, right? So with output integrity, what we're trying to answer here is how reliable and accurate are the agent's outputs. So we're trying to really focus on the agent outputs to sort of get these qualitative insights into their behavior. So we're trying to answer questions like, is there drift in the types of prompts you expect, or concept drifts in how your model is responding, right? These are not things that you can just pick up using operational observability metrics, right? So it's going to be things like, is the LLM responding in the right tone? Are you seeing divergences from your anticipated topics? These are all things that we're trying to analyze and track using output integrity observability. So YLabs has a really nice, so they call YLabs language toolkit, LangKit, right? And so they're able to add input. I would consider these to be more evaluations at this point. But they're able to track all of these different metrics, so hallucinations, injections, private entity identifications, sentiment. So they're able to integrate all of these sort of metrics that they can gather related to output integrity based off of from your agentware, right? And you can then make some sort of evaluations based off of these metrics that say, oh, is my sentiment drifting enough that I need to do did I need to take some sort of action to address it, right? Second one, so semantic feedback. So what did we think of the agent's actions, right? That's the question we're trying to answer here. So this is grouped into 3 different types of feedback. So explicit feedback, which is going to be direct things, like the user gave this answer a thumbs up, thumbs down. We're going to do implicit feedback. So this is sort of gathering what the user did with the agent's response, right? So did they copy it, save it, dismissed it, didn't take it at all? We'll see a good example for that in a second of GitHub Copilot. And then free-form feedback. So basically, did we have any sort of concrete corrections that the user might have made to the output, right? And over time, this really helps us to gauge the efficacy of the FMware outputs, right? It's really answering, okay, what did the user think of this? Are we doing a good job? If we're not doing a good job, we're able to sort of track this and take action because of it. Now, there are also some challenges. So as these systems get more and more complex, right? Multi-agent systems are going to get more complex. It's really hard to figure out, okay, what did the feedback actually mean for the agent's response, right? Like I said, if you have an output of an agent that is based off of previous agents, right? You might be flagging the output from that bottom agent as being bad, but really that agent's performing fine. It's a previous agent that's actually doing that actually needs to be improved, right? So this comes with, so like I said, pinpointing improvement areas in multi-agent systems. And then, so the complex agent dynamic adaptations, agents can change, right? They can change their behavior as they sort of go through or as they sort of evolve. So it's kind of, it obscures it quite a bit on what the user is actually trying to evaluate, right? So these are all challenges with semantic feedback. So if we look at some concrete examples, right? Most people would have seen ChatGPT, so bad response, regenerate, right? Human loop, so this is another nice framework. So this one actually offers an evaluation suite to measure and improve LLM performance. So they're able to make it really easy to sort of track how the user interacts with agentware. So they can track, click button, save, selected. They can track whether users are reporting hallucinations or repetition. And then same thing, upvote and downvote. And then GitHub Copilot, so that's actually a really interesting one. So I think we've mentioned something about the acceptance rate of GitHub Copilot and how it's using that to track the efficacy of its suggestions. But it actually goes a lot further. So there's a nice blog post that they reverse engineered GitHub Copilot. And I'm trying to remember so they reverse engineered GitHub Copilot, and they found that there are actually a lot of observability metrics that they're tracking with this. So basic one is acceptance rate, right? Did the user accept the suggestion? if the user accepted the suggestion, they're going to track over a specific period of time the edits that were made to that suggestion to see how much the user actually changed the suggestion, right? So if the user just accepts it and then that's it, that was a very good suggestion. But they might, for example, edit this over time. So let's say after 20 seconds, there's about a 50% similarity between the original suggestion and what it is now. After 40 seconds, it might be down to 30. So this is just an indication that says, oh, the user might have accepted the suggestion. It wasn't great though, right? They just took the idea and then started changing things. But these are all cool little things that you can begin to gather with semantic feedback. And then, yeah, so the third one, right? So reasoning paths. So this is actually the one that kind of, I'm trying to understand what the agent's doing, right? If the agent outputs something, I don't really know why it's doing that, right? And so the reasoning path is trying to answer what's the logic behind the agent's actions, right? So it focuses on understanding how models reach specific conclusions, tracking these explicit reasoning processes. So we've already mentioned a bunch of papers, right, on LLM reasoning, and then plenty of people have heard of the OpenAI O1 model, right, which is essentially what's being called a reasoning model at this point. There's plenty of research on how reasoning is going to be improving agents' performance, right? It's not always possible, though, to get agents to output their reasoning. So we mentioned this earlier, right? The act of asking an agent to output its reasoning process actually changes the agent's behavior. So if you were to prompt an agent for a question, or with a question, and it gave you the right or the wrong answer, if you follow that up with, okay, are you sure? Let's think about that. The agent will come back and be like, oh, sorry, I made a mistake. Here's the correct answer, right? And so if we ask the agent to output its reasoning, it doesn't necessarily mean that the agent's going to, so it doesn't necessarily mean that the agent's going to be performing as it would have if you haven't, right? So this is called the observer effect in physics, right? That's the little analogy we make. And then also, right, so these agents, it's AIware, right? So they might be tied to other systems that might not be able to handle the outputs from the reasoning. So in this example, right, the agent might be expected to be output JSON format. We can't necessarily ask the agent to include the reasoning on why it's outputting the JSON it is the JSON that it is, if that JSON is being used by a downstream system, right? That'll break the whole compatibility chain. And so these really limit the agent's ability to provide sort of a comprehensive explanation without compromising its primary functions, right? And so how do we move forward with this? So I'm going to be talking about Watson, which is a framework for reasoning path observability. This is from a paper we had recently submitted. And so this is how we're beginning to address the challenge of reasoning path, right? So what's Watson, right? So it's designed to observe an agent's reasoning process without actually interfering with its behavior. So this leads to a good example of what we can do with reasoning observability. So how do we do this? What we do is we have a surrogate agent for parallel reasoning, right? So surrogate agents have been used in machine learning systems in the past, but but what we do is a surrogate agent, we operate alongside the primary agent and then replicate its completion while reasoning about how it reached that completion. So you might have your primary agent, right, that outputs a result. This internal reasoning process, we can't see it. Unless we want to affect the output results in some way, we're not able to see this. And the user might be wondering, okay, why did the agent respond like that? So what we have is a surrogate agent, right? The goal is not to solve the problem, right? It's given the same problem as the primary agent. Our goal is not to solve the problem, but to arrive at the same result as the primary agent. And while it's doing this, we're asking the surrogate agent to reason about its decisions, right? And we can take this reasoning, give it to the user to answer the question of why did the agent respond like that. So if we look at just a bit more detail, I'll go through this So, surrogate agent, right? We need to have an identical configuration as the primary agent. The goal here is to try and explain why the primary agent gave the result it did, right? To do that, we need the surrogate agent to be identical as the primary agent, right? And then once we have an identical surrogate agent, we take the prompt, the replicated result, and reason verbosely about it, right? We do this multiple times. So the goal is to try and figure out, okay, what's the reasoning path that the primary agent took? So we generate multiple of them just to get as many potential reasoning paths as we can. We summarize them and then give that to the user, right? We do some validation between to make sure that the reasoning is actually in line with the primary agent's prompt and answer. What we mean by this is that we take the ideas that are presented in the reasoning process and confirm that they are in line with the sections of the prompt that the primary agent paid attention to. So if you remember, we were talking about prompt explainability, right? From a couple days ago. I forget whose talk it was, but we were talking about the prompt explainability. What sections of the prompt are important to the primary agent, right? So we verify that the parts of the prompt that the primary agent was paying attention to are actually present in the observed reasoning processes. So this just means like, if the primary agent was paying attention to a specific section of the prompt that doesn't show up in our summarized reasoning, we know we have a problem here, right? Because that shouldn't make sense. The surrogate agent should not be generating ideas that didn't actually mean anything to the primary agent. Once we have that observed reasoning process, we give that to the user, right? So that's going to answer the question of, okay, why did the agent respond like that? Now, to actually generate the reasoning, right? The goal here is to generate a reasoning that ties the initial prompt to the final answer, right? Essentially, and so what we're doing is we're filling in this middle section. And that's actually a technique that was presented in this paper down here, where we take a prefix and a suffix, and then we generate a middle that ties these two together. This is used primarily in code completion, because a lot of the time when you're writing code, right, you're going to have this prefix, which gives us some context, and then some suffix, and you're using this generated code to tie these two together, right? So the first time I actually got Copilot to do a suggestion here, I didn't have the return result section, right? And so because I didn't have the return results section, it had with open file yada yada return file, right? And then so return file. So now that I have the suffix though, it knows that I want to assign, I want to return result, and so it's assigning file to result, right? And so this is an example of how these language models are actually trained to recognize this. So they'll take their training data, break it into documents, and then split it up. So into a prefix, a middle, and a suffix. And then when they're going to train the model, they'll actually switch the middle and the suffix. So quick brown fox, a lazy dog, and then it will get the model to try and generate this jumps over section. And so that's how it's being trained to fill in these middle sections. With Watson, right, the goal is to generate the reasoning, right? So the prefix is going to be the initial problem, or the initial prompt from the primary agent. The suffix is going to be the final answer from the primary agent. And then we're asking it to generate the reasoning that ties it together. We have to add in this little section here just to make sure that there's a concrete tie between the prompt, so the initial prompt and the answer. And then the agent is able to actually generate reasoning that led the primary agent from the initial prompt to the answer. So this is just an example. So this is a concrete example that I paraphrased a bit to fit on the slides, but it's an actual example of how this is working, right? So this is from a question from an MLU data set. Are either of these two scenarios morally wrong? So I asked for a cigarette from the guy outside the store, and then scenario 2, when the security guard left his post, I pocketed a rare coin. The response the agent gave me, wrong, not wrong, is correct, right? One of these is wrong and one of these is not wrong, but it's in the wrong order, right? So scenario might not be socially acceptable or healthy, but it's not morally wrong. Scenario 2 could be considered morally wrong according to whatever. But the answer is incorrect, right? And so we might be confused on why this is happening. What we can do, so the surrogate agent, we actually hand the prompt and the response to the surrogate agent, and we're able to generate this reasoning, right? So this is actual output from the surrogate agent. The highlight in here is the wrong, not wrong option. It states that one of the scenarios involves something clearly morally wrong while the other does not, and then not wrong, wrong, similar to option B, right? So this tells us that, okay, the agent's not actually paying attention to the order. And so based on the generated reasoning, it seems like the agent is not considering the order of wrong, not wrong options. What should I do about it? I should instruct the agent to make sure it takes that order into account. And so the common reasoning paths, right? So I mentioned we're generating multiple reasoning paths for the summary. So same question, different scenarios though. So scenario 1, I bought an old pickup truck for work. Scenario 2, I looked up at the gorgeous waterfall and threw a rock at it. The agent output, so it just gave not wrong, wrong, right? Which doesn't make sense. That doesn't seem right. Why did the agent say this? And so what Watson actually does, so it'll generate multiple reasonings to try and figure out the common reasoning paths that this agent might have took, right? And then so once it actually generates the summary, right? So this is fine. Scenario 1 makes sense. All of the summaries actually highlighted that causing harm or destruction to nature is generally considered wrong, right? Which, like, most people would agree with that. But if we look at the actual scenario, I looked up at the gorgeous waterfall and threw a rock at it. So it seems like the agent is considering that to be harming nature, right? And so they're all considering throwing a rock at a waterfall to be causing harm or destruction to nature. I should clarify what this means, right? So the goal of Watson, right? It's not really to like sort of solve the initial problem. It's just to guide the developer to sort of debug these prompts where the agent might have gone wrong and has some insight into the actual reasoning processes of the primary agent. Yeah, so I'm running a little short on time, but so we can use Watson for identifying and correcting reasoning errors, right? And so the value that this really brings, right? So if we can observe these reasoning paths, we're able to diagnose these issues, right? So we're able to improve prompts and stuff. One of the main things we can actually do though, right? The agents can benefit by gaining a deeper understanding of system behavior. And so they can actually take these reasoning paths, right? And use them as context to sort of improve their behavior as they evolve. And then so if they're able to actually improve their behavior, right? In multi-agency systems, they can improve other agents' behavior, right? So if we can have agents that are observing and reflecting on each other's reasoning paths, right? We're able to actually go through this collaborative refinement. And then these agents and these AI systems as a whole can sort of continuously improve as they evolve. And this is just going to get more and more, I guess, important as we move to these reasoning models, right? And so we're sort of just trying to get, observe these agents reasoning, observe the reasoning path of agents so that we can have a positive feedback loop, right? And improve these agents' performance as a whole. Okay, so I want to leave a bit of time for questions, but this is what we talked about today. So we'll go through that. Some other points just to mention here. So this is our paper that I just discussed Watson about. These points are also mentioned in these two papers as well. So you can follow on with there. Sorry. You can follow along with there. They mentioned some of the challenges, and the opportunities with the research work that we're going with that direction. Yeah, and so I'm happy to take any questions.
Thank you, Ben. Okay, we are open for questions.
You have a very interesting talk, and I learned quite a bit. But I guess my question is this last bit, like trying to train like a cognitive agent, trying to explain the rationale and so on, right? So I'm just wondering, like, why do we have to do this? Instead, we kind of always prefix it with, let's say, a planning agent is spitting out the plans. Just as we used to do logging, so we spit out the plan. You can have the plan and then ask the agent kind of execute based on the plan, which I think these kind of AI judges or cognitive agent is much easier to check and explain based on that. Because right now it seems like you're trying to find some way to understand how the black box works, which may be true or may not be true, and it takes a while to kind of learn, right?
Yeah, so it's definitely a good question. So what we're trying to look at here, I guess, is at the level of what we can't actually explain. So it's the level of asking an agent why it made the decision it made, right? So the example you gave was a planning agent, right? So why can't we have a planning agent just come up with this plan, give it to other agents to sort of do what the plan specifies, right? What we want to actually try and observe, right, is why the agent took the actions it did based off of the prompt. So for example, if the planning agent gave a plan as a prompt to one of the agents, we want to be able to see, okay, regardless of what was given to it as the prompt or the plan, how did it actually reach that conclusion? A different example would be for reg, right? If you were to give an agent some context, right, in its prompt, so in context learning, and it was to output some response, right? Can we actually see, like, did the agent really use the knowledge that was in the prompt, right? So can we actually see that it used the correct knowledge? Which ones did it use? And the reasoning process is sort of a way to use as a proxy to actually confirm that, I guess. Right? So we're trying to go at that level of, okay, that black box level of regardless of what it's given for the prompt, how did the agent actually interpret the prompt? What knowledge did it use to actually come with the completion? Does that make sense?
Yeah, but again, it's more about just think about the way debugging, right? So debugging usually works, you break down into the things and then you ask them execute step by step. Instead of doing so, anyway, we can talk offline. It's just counterintuitive to me.
Sure, okay.
Maybe we're there. Thanks. Thank you, Ben. So maybe this is more of a clarification question, right? So the result that you're trying to get, is it the answer or is it the reason?
No, so it's the reasoning. So are you talking specifically with Watson?
Watson, yeah.
Yeah, so it's specifically the reasoning. So we already have the answer, right?
So your primary agent is also a reasoning agent.
Yes, it could be.
It could be, or is it the reasoning agent?
It could be.
Okay.
Yeah.
Okay. Maybe I'll ask you later.
Yeah, so thanks for the talk. My concern also follows the first question. We know that if you give the same prompt several times, you will not guarantee idempotency or any kind of deterministic view. Now, when you look at reasoning, it has some kind of cognitive thought process where you can arrive with, let's say, inductive reasoning or deductive reasoning. But in this context where there is a lot of variability, how will you assert? It can take a different path depending on the data that it referenced at that point to arrive at a certain conclusion, which might be a little bit out of the quadrant that you mentioned, like correct but not, like socially correct but not accepted, in those kind of things.
Sure.
How will you assert that this reasoning is not only correct but logically backed with the data that it was?
Gotcha. So, okay, so I just so I understand your question correctly, it's how are we actually confirming that the reasoning is in line with the prompt and the resulting completion? Is that
with the exposure itself, where because the model can use different paths of knowledge to arrive to that conclusion.
Yeah, so we've tried to sort of address that by generating the multiple reasonings. So a lot of the times, the self-consistency idea from the self-consistency paper, right, is to generate multiple reasonings and try to, just so we get as many potential reasoning paths as possible, right? So we can try and figure out as many of the paths that the agent would have taken to get from the prompt to the completion, right? The idea with summarizing it is just so that it's because the goal here is debugging, right? So like we're trying to, so in this context, we're trying to debug any of the issues that, debug the issue that might have led to the confusion from the human foreseeing it, right? Okay. So we're trying to present that in a debugging fashion in this context, right? Yeah. But so we summarize them, right, to get the main points, and then any sort of unique, as we do include any sort of unique points that might have been generated in the reasonings. So any of the unique points might not have necessarily been as common or likely, right? But they're still worth mentioning to the user, just in case, like, you know, something might have come up with it. Does that make sense?
Thanks.
Okay, so let's thank Ben.
Cool.